The co-host, please let in anybody else who comes in, please.
Sure.
So today it would be Vaishnavi who's Vaishnavi.
Yes, ma'am.
Start whenever you want.
Yes.
So is this available on YouTube afterwards? I mean, or what? How does it go?
A very good evening to all. I'm much delighted to
One second, Vaishnavi, Dr. Suprit was saying something. Sorry, you were saying something, Suprit?
Yes, I was asking, is this available on YouTube afterwards? Or,
if you want to list, I put it on YouTube just so that there's a recording. But yes, it's available.
Okay.
I can share the links with you.
Sure. No worries.
Yeah, wonderful. We'll do that. Yeah. Sorry to have interrupted, Vaishnavi. Please go ahead. Vaishnavi?
Yes, ma'am.
Go ahead.
Very good evening to all. I'm much delighted to offer a warm welcome to each and everyone who have joined in this meet. Today, the topic of our discussion is the most awaited and suggested one, that is astrophotography. And I'm glad to say that here we have Dr. Suprit Singh again, again to take us to the beauty of space photography. And he's an associate professor at IIT Delhi in the Department of Physics. Welcome, sir. And I extend a hearty welcome to all the faculty members, participants, and coordinates to the session. And if you have any doubts, you can write it in the chat box. We'll discuss it at the end of the session. And now I invite Dr. Suprit Singh to take over the session. Sir.
Suprit, are you here?
Yes, I'm here.
Yeah, please.
The mic was muted. So
Yeah.
thanks so much for the nice introduction. And this is the part 2 of the talk. So I believe everyone has gone through part 1. And so therefore, I don't need to go over it again. So part 1 was basically we're looking at different aspects of astronomy, as in more sort of related with visual astronomy, what we like to see in the what all is there in the sky, how we can basically understand various processes and various phenomena that go around. And this one, so I'll share screen now, and is to do with astrophotography. What if when we start imaging? So is my screen visible?
Yes, it is.
Okay. So in between, so I was, so last time as we spoke, I was in two minds whether to, wait a minute, is this, the date is not correct. Today is supposed to be 18/20/21. Yeah. So, yeah. So actually the disclaimer is that this talk was also given on June 18, 2020. I just had to flip one number.
No.
Yeah, but I mean, not it's not the same talk. There's a considerable amount which has been added. So you will see whether these things come in, because yeah. So I was in two minds whether to talk about the way things I mean, all these instruments in astrophotography, the way they work, the theory behind them. And the second thing was to actually bring you directly to the field, as in get you all started. So I figured, I mean, I don't advocate doing these things separately. I mean, I really want that everyone should know both the aspects together. It's a marriage of both together, which yields successful astro business. But nevertheless, due to time, I'll possibly skipping on some more details, but I'll definitely mention the jargon so that you can all go in and check those things out. But the talk will basically be to bring you directly into the field and get you started right now. Well, not right now, it's not dark yet, but still. But if you're interested in the solar physics, solar astronomy and solar photography, you could start right now as well. So astrophotography, what you need to know: capture the skies with your in-home mirrorless or DSLR cameras. Of course, that was the original one where I wanted to talk more about DSLR cameras, but now I've also added about what sort of amateur astrophotographers would do and how it will sort of develop into much more professional astronomy and data gathering. So you'll basically see that in the talk. And at some point, actually, I'll switch on my webcam. Hopefully okay, what I'll do is I'll switch off this presentation because I need to conserve the bandwidth. And I have my setup over here. So we'll do a walkthrough. So, okay, so I've again run into that same problem of why does Zoom do this?
What's happening?
I'm unable to advance my slides. So I think someone will need to, it's frozen. Someone will need to.
No, you can just stop sharing and then reshare.
Okay, let's see. So is it stopped now?
Yes, it has stopped.
Okay, so hold on for a second, then let me start resharing it. There is the, yes, so Zoom and start. I'll share the whole desktop. So I guess the desktop would be visible now, and I can paint everything. Yes, good. So we saw in the last talk that night skies are not really dark. We need to switch off all the lights, and the stellar lights come into play. And now, in order to get most out of the stellar light, because after all, you're capturing photons, which are really from, I mean, these are faint objects, and they're not really faint in the sense the intrinsic luminosity is really bright, but they're so far off that the flux falls off. So definitely you're doing some photography here, which is very much different from your usual daytime photography. Daytime photography is something where ample amount of light. The whole scene is lit, and so there's a lot of signal and very much less noise. So here, the signal is very less and there's a lot of noise. There are different sources of noise. A lot of sources of our own atmosphere in the way it scatters light from light pollution, which terrestrial lights coming from terrestrial lights. And then, of course, there is thermal noise in the sense that there will always there's a heat involved. We're working at some finite temperature, and the hotter your temperature you're working in, there will be fluctuations, and these fluctuations in the sensor cause noise. And that's thermal noise which will be there. And then there's a circuitry which is involved in sensors in the cameras, and you don't have anything which is ideal, and so there's always some sort of read noise which is associated with how the CMOS and the CCD sensors inside these cameras, those are the technologies, the semiconductor technologies, how they are read. So how the data is read. I mean, essentially what happens, you have a photon which strikes it, and first the photon is it's a light electromagnetic wave. So it knocks off, I mean, the only thing it attracts is electrons and stuff, the charged particles. So it knocks off electrons. So, and hence you convert light to current. And it is current which gets filled up. So every sensor is made of pixels, small sites in which these currents are generated. And that current is I mean, as the pixels fill up, this current is, I mean, you exposing for a particular amount of time. That is, you've kept your shutter open and you're grabbing these photons, they fill up, and then when the exposure time is over, that is, suppose you set your exposure for 10 seconds. So the shutter is open for 10 seconds. It takes in these photons, and then the amount of current that you get is, of course, proportional to the amount of photons that you got, roughly speaking, ideally. And that current is read from these individual pixels. Now, it depends on the technology, how they do it. For a CCD, the older CCDs which were there, you had to read them row by row. So all row pixels across. So it's a matrix, right? You can see a rectangle. Sensor is like a rectangle. So it's a matrix. So you read all of it row by row. CMOS allows you to read pixel by pixel. So there's a difference in technologies. Anyway, so that's cameras. And so what are the basic grabs which you need when you want to start shooting? So I told you, you don't need really, you can go from anywhere from so starting equipment to, so science can be done at all scales. And even astrophotography. So you can, you don't need too much of a thing. Even if you have your own daily use camera, the DSLR, it would work. Lenses, particular type of lenses are more suitable than others. We'll come to that, which ones. You need a tripod, of course, to keep things stable, ball head to move things around. Intervalometer, don't want yourself to be standing there pressing the shutter button every single time. Also, because whenever you press the shutter button, you will introduce a jerk. You don't want anything like that. Intervalometer is basically you set up how many exposures you want, what are the timings. Let's say you want to take 10 exposures. I'll come to why we want number of exposure, not just one single photo. And essentially to reduce, to get high signal to noise ratio. That is, it's a matter of statistics. If the more you collect the data, it's like random, the noise, it decreases the more you sort of do averaging or some sort of statistics on it. So you need to therefore take a large number of images and then get a sufficient SLR. So that is the signal to noise ratio. Mobile apps like Sky Safari and all, they're useful. If you have if you know star catalogs and all, you can read them to know which objects you're shooting, where it is, and all that. So you know those ideas. You have an idea about that. Computer and softwares are necessary. Not always. Suppose you're shooting with a DSLR or something, you'll get, everything will be stored inside this DSLR. There's an SD card there. But if you're shooting with some other camera which does not have a storing capacity or something like that, it's connected, hooked to a computer, and the images can be stored in the computer, because these images will be processed. You need to do certain amount of processing, and of course, coffee to keep you awake.
Suprit, anyone who says coffee, I know I can trust your photography and whatever else you're going to say.
That's good.
Yeah.
Yeah. So yeah, so that's very important. So camera. Now, what type of camera do you really want? Now, if people will say there's some sort of a special camera or something, no, well, not really. Any mirrorless or DSLR camera will work as long as it has a manual mode. Like I have a Sony A7R II. That's a DSLR. It's a mirrorless camera. I'll come to what means by mirrorless. So, so any camera, as long as it has a manual mode and allows the bulb exposure setting. The reason is we don't want to take, so usually in a camera, you'll have particular amount of exposure, like 1/200th of a second, or 1/15 of a second, or 1 second, or they'll max out at 30 seconds. But sometimes you need pictures of more than 30 seconds. Like this would be even 5-minute exposures sometimes. Okay, so those are not there in the camera, but there's something called a bulb exposure. So if there's a manual mode, you switch it to it goes like M on the dial, and you switch it to manual mode, and then you shuffle through the exposure dial, and it will lead to what is called a setting called bulb exposure, which is beyond the 30 second. Bulb essentially allows, it basically tells the camera that it waits for a trigger. And that trigger is given by intervalometer, which is connected to the camera. So you collect, so intervalometers, again, there are different, so these are proprietary. All manufacturers make their own different cameras. Of course, they don't want uniformity for their business reasons. But so you will get intervalometer for a different camera. So you know which camera you have. You have a Nikon, you'll get a intervalometer for a Nikon camera or Canon or Sony. And so that intervalometer, what it tells, it basically sends a signal to a trigger to the camera, open. So it opens, and after some time, whatever timing you've set, let's say you set 1 minute. After 1 minute, it will send another trigger to the camera, close. So that allows long exposures, and it can do that multiple number of times. So it can do 1 minute, close, wait for like 10 seconds, and then again 1 minute, open, and then close. So it's like a square wave.
Is it something like a programmable remote for the?
Yes, it is. It is a programmable remote, but much simpler in programming. It's just two. Yeah. I'll show you one. Okay.
Okay.
So yeah, and even Canon. So yeah. So what type of cameras? So I'll be like, do I need to buy a latest camera? No, you don't. I did. So even this Canon 450D, this camera is from 2008. Believe it or not, I bought it for $150, secondhand. Okay, and worked really well. Now I'll tell you what about it. So these cameras usually, because they're designed for our daytime photography, all the manufacturers, they will install something called LP filter just in front of the sensor. Basically it does is it cuts off UV and IR. Okay, so they don't want the camera to be, the sensor to be flooded by UV IR, only the visible part. So there's that thing which filter which is there in this in front. Now it's fine. I mean, not a big problem. I mean, after all, we are doing optical astronomy. The wavelengths lie in visible band, but the H alpha, as I mentioned previously in my previous talk, 656 nanometer is very near the infrared, almost goes near that. So there's a transmission profile of these filters which they usually attach, and often it happens that it sometimes clips. The transmission doesn't go to unity in the optical directly immediately. It's not like 0 in the infrared and 1 in the optical. It has a certain profile. Wish I could have shown this there, but nonetheless, it has a certain profile, and so it clips off certain H alpha. So this is what people do is they take these cameras and they modify it. But essentially it means is open it up and remove that filter in front of that. It's a tedious job. I did that with this 450D and removed it, so it became a modified camera. It requires took 6 hours basically, and at the end you get a camera which is naked. So there's no filter on top. The whole sensor is getting all the wavelengths. Of course, you don't. So then it's called a full spectrum mode, in the sense it's no matter what falls on it, it'll take it. But still, infrared and UV do create problems. Like there you'll find halos in front of stars and stuff like that. But after all, our atmosphere is it's bad for IR and all that. So there are special UV IR cut filters for astronomy, which will not have that profile problem which I was telling you about. They will allow full 100%, I mean not full 100%, but close to 100%, around 90 or so % transmission for H alpha and those wavelengths, and those can then be used in front. But, I mean, you don't fit them inside the camera, but there are clip-in filters which can be fit in. There are the filters. I'll show you the type which come in. So that is something which usually one does, but you can definitely use your unmodified cameras as well. And these are entry-level cameras like 450D, Nikon 3000 series. 3100, 3200, they definitely can. You don't need to shell out, 2 grand for, I mean, 1 lakh or something, 100,000 for a new camera. Even cameras worth, for 30,000, the entry level cameras work really well. So, manual mode means you set the ISO, shutter speed, and aperture as required. So, in the sense that there's something called the ISO, which is now this is a remnant from the film days when there used to be cameras with film. Films used to be of certain ISO setting. So, what meant was film with higher ISO was more sensitive to light. So as ISO was basically considered as sensitivity. But now you don't have films anymore. We have what are these CCDs and CMOS sensors. So usually you'll find a lot of photographers and all that. They'll say, okay, this still the sensitivity. It's not really sensitivity. It's just a gain. It's just a multiplicative factor. Okay, so essentially you find that you have, let's say 10 photons which arrive on a pixel and they produce a certain amount of current, and you essentially multiply that current by a factor of 2 or 3. So these are just multiplicative numbers in order to amplify it. So it's an amplifier kind of a thing, gain. So generally speaking, oh yeah, I'll have to go into camera basics for that. I don't, okay. So generally speaking, you need a certain gain in order to, okay, let me give you a situation. So the situation is, let's say you're shooting a Formula One race. And so in order to do that, I mean, things are moving really fast. You need to be very fast. So your camera cannot open for a large duration. You need to be like 1/200 seconds or even less than that. So since you're opening your camera for such a small amount, of course it's daylight because there's a lot of light which is there, but still the exposure time also matters in how much light you are letting in. So you're not really letting in a lot of light when you're opening for a very small time, that is shutter speed. So therefore, what you do is you increase your gain value or the ISO value so as to multiply whatever photons. So even if there are 10 photons, you multiply it. So basically it's like amplification. You amplify the current and hence you will produce an image. Of course, because you had less number of photons seep in, there will be noise. That is very much understandable. Now, people will usually say, hey, I mean, high ISO gives large noise. No, it's not the high ISO that gives large noise. High ISO, even when there are lots of photons, will not give you any noise at all. Okay, it's because usually when you go to high ISO, you will also reduce the shutter speed. Because if the shutter speed is increased, I mean, it's obvious. Like, I mean, in the sense that there'll be many photons, your whole picture will come out to be white. So you definitely, it's the less number of photons that cause noise. It's again, matter of statistics. So, so you use high gain value there, high ISO value there. Even in astronomy, since we are anyway getting less number of photons, so it's advisable that you go to high ISO, high gain values. People will again say, this is again a difference between normal photographers or normal astrophotographers or some people who know what actually it is. Well, you are really, again, you're looking at faint objects. What do you expect? There will be noise, definitely will be noise. So you handle it scientifically, handle it using statistics. That is, you take large number of exposures and average them so as to improve the signal to noise ratio. So that's that. Aperture is what is the diameter of the lens, how much it is open, how big is the aperture, same as the aperture of our eye. And so every lens has an aperture, and so you need to have manual mode basically allows you to set all these things independently. Camera doesn't do it for you. Otherwise, there's a P setting where camera automatically judges according to what environment it is. There's a meter on it, and it sets things for you. Right? So, but the camera doesn't know astrophotography. It is dumped there, so we set it ourselves manually. Then there's something called focus peaking. you need to focus on objects in the frame. And for that, I mean, anyone who has tried focusing in night knows what are the issues here. You don't see the objects, so what will you focus on? Um, there are aids to in order. So there are you're basically looking at stars which are point objects. So there are things like Bahtinov mask, which is diffraction mask. Basically, what it'll do is it will you'll see so the cameras have what is called a live view mode. You open it up, basically it shows you what actually the camera is seeing live. Rather than so DSLRs usually come with a viewfinder, which is an optical viewfinder. Okay, that is you have a prism in front, you have a mirror in front of it, and the mirror, the light coming up from the lens strikes the mirror, which is a 45-degree, moves up to the optical viewfinder, and that's how you see that what is in front of you, what is the camera looking at. Now, so that is essentially the same. I mean, if you point it at any object at night, you will not see anything, because that's the same thing which you see using your eye. Everything would be dark in an optical viewfinder. Now, the latest so either the cameras will have live view mode, which you can enable, and then on the LCD behind it, you will see what is the camera looking at. That is slightly, as I said, amplified, because you set up your settings, so you will be able to see much more than what the eye normally sees. So therefore, that will allow you to focus on stars. You will basically take a look at. You will basically be able to see stars. So you see where it is in pinpoint focus. The Bahtinov mask basically allows you fit this thing in front of the lens, so it makes spikes on the stars. I should have added this thing. Wait, I can do it. So is it? Oh, it stopped sharing.
Yeah.
Yes. So that's okay. Yeah. So let me share screen. Okay. Yeah, you'll be able to see. So this is something which is a Bahtinov mask. So you see these spikes. So this tells you whether it is in focus. All three spikes align together. And if it is out of focus, one line would be outside. So you see two of them forming a cross. The third one is slightly off. And this is again outside focus. It is either here or there. When they're all three are aligned, they're in focus. So this is a Bahtinov mask. These can easily be 3D printed. So, there's something called.
But how do you get that? I'm sorry, can you just?
Yeah.
How do you get this Bahtinov mask again on a normal camera?
Oh yeah, so it's like this. So you fit it on the lens in front.
Oh, I see. So
you get it made of the size of the diameter of the lens. So you can simply put it on in the front, and when it's focused, you just put it off.
This is custom made, or like you get them off the shelf?
Yes. So you just go to thingiverse.com and type Bahtinov mask, and you'll see 3D print designs over here, which you can also customize for your lens. Suppose I have this particular lens, so I have one with this 135mm, but there are designs where you can modify it according to customize it according to your diameter, and then print it.
Okay. Thanks.
So, but then the newer cameras also have something called focus peaking, where the camera itself has a technology which shows colored highlights on objects which are all focused. So it will show that these things are now in focus. But of course, that is using some sort of computer processing. So it's not, I mean, I found it trustable, but still it's better to also use this Bahtinov mask aid, which is something which definitely low. It is in focus. So, but this focus peaking does help. It helps enormous deal. It's there. So for a DSLR, if you have an optical finder, do so this is just a advice. Cover it with a dark cloth using an exposure, because you will have light also going through it, and that will go to the sensor. Generally, in daytime, again, it doesn't really matter. It's a whole lot of light, but during night, any contamination would be too much. So cover the optical viewfinder. If it's a latest camera or something, it has a electronic viewfinder, then there's nothing like, you don't need this thing. So we shoot images in what is called a raw format. Now this is like a misnomer. It's not really true raw. So what raw means is what it's in actual data which is there, which you have retrieved from the sensor. Now generally in all these consumer cameras, it's of course there is a raw format, and there is also a JPEG. JPEG is processed image already, which is processed. So everything is basically all information is gone from it. You cannot change dynamic. So essentially, there are things like dynamic ranges of the sensor as well. Now that is there's it has recorded some data. It has recorded how many number of photons were striking a particular pixel. So you can process your image therefore accordingly. But JPEG is something like baked. Like there's some processing which has been done, and now so there's a loss of information which has happened. So you shoot in raw format. All cameras allow shooting in raw format, but they're all different. Like for instance, Canon have their own .c-raw, Nikon have NRW, and Canon and Sony has ARW. So they are not true raw formats. They also have some slight bit of processing done onto them according to whichever camera manufacturer it is. True RAWs usually come in the actual cameras which are dedicated for CCD cameras, astronomy purpose, or medical. I mean, the dedicated cameras, not consumer cameras. So, but still, they are close to RAW. The consumer camera RAWs are quite close to the RAW. There's a certain thing called clipping, which they do, which is essentially the dark. The dark site areas in your image are made slightly less dark. They're not, so all pixels will, so there won't be any pixel which will have 0 photons on it, right? No matter what, there'll always be a fluctuation. So it has to, and there won't be a negative fluctuation, there will be a positive fluctuation. So there will always be something on that pixel. So they will also add, so basically they'll take this, the whole image is like an array, right? One number for a particular pixel. So from 0 to 255. So let's say a pixel has 48, then the next one is 53, and so on. They will basically add an offset to the image like +10, and the whole image would be shifted by +10. That is what they do. So, but we don't know what that offset is. Otherwise, we would have subtracted it and would have gotten a true RAW. But that is, they compute this offset by some nonlinear processing. So that's why it's not a true RAW, and we cannot really retrieve back that. So, but we definitely shoot it into the astronomy images, shoot them in RAW, and then we process them and we make our own JPEGs. We will not let the camera make our JPEG. Cameras don't know how to process astronomy images. They only know how to do daylight. There's something about white balance. It doesn't really matter in RAW because it's a processing variable. It matters in JPEGs. Next comes, so that tells you all sorts of cameras are usable. Lenses, I need to keep track of time. Lenses, any lens will work as long as it has least imperfections, such as coma. This can be chromatic aberration. So you need to find lenses which have least amount of these imperfections. They essentially will either, of course, probably see a review article or something. They show how the lens responds to point sources, like stars are point sources. So there can be these chromatic aberrations in which not all wavelengths are focused at the same focal plane. So you might see there would be a fringing in around stars, like purple fringing or something like that, or stars near the not in the center of the frame, at the edge of the frame might be elongated. That is called coma aberration. Well, they would be there in all optical components. It's just that you want something with least amount of these least amount of imperfections or aberrations.
That was precisely my question, because I don't think there's any lens which doesn't have the fringing and vignette in.
Yeah, so it's about tolerance. So the idea is so there's a lens. Every lens has a resolving power, and also there's a resolution of the sensor itself. So so there's therefore a tolerance which would be there, and wherein you will not be able to see that this stuff. But then there are lenses which give awful lot of fringing, and those are simply unworkable.
Okay.
So I'll show you the lenses which I have, which are really good, which I can sort of recommend for these things. And then there is f-stop, which is what is the aperture of these lenses. So you really want them to be so this f-stop is usually there in lenses. It's not really there for telescopes. Telescopes have fixed aperture. Whatever is the diameter of the objective, that will give you what is and the focal length, it'll give you the aperture f number. But for lenses, you have a iris, is the same thing coming from our eye, which can open, close down and open up. So wait a minute. I think at this point I should probably switch from the stop to an actual field demonstration. Okay, so I need to. It's the camera. Start a video. Okay. Yeah, visible, right? Okay, good. So whether it would be visible. If it not be visible, then we'll sort of not. So there is a F number on it, which controls the.
You can stop sharing the screen, then we can see you on the full screen.
Okay. Okay, maybe.
Just stop sharing the screen for a second, and you can go back to it.
Yes, I can do that. Stop. Pause. Share.
Yeah, that's great.
Yeah, so you can see through it, right? This is a full open lens, and now, yeah, now I'm closing the aperture. I don't know how much is visible. But this is the aperture which is there. So one needs to have, yeah, so now it's, so you need a fully open lens so that, yeah, so there's this aperture where, so you generally need lenses with wide open aperture. So there's something called f-stop. This is sometimes necessary in the sense that there are lenses. So you will see whenever you go by a lens, there are two numbers. One is its focal length, which they call it focal length, 35 millimeter, let's say, 35 millimeter lens. So it basically tells you it is on a full frame, camera, it has a certain field of view. So that is a 35 millimeter field of view. And then there would be there'll be a number, it's called 35 millimeter f1.4, let's say. So that what that means is that its aperture is 1.4, means its aperture is what is the diameter of that. So if you take the ratio of the two, 35 divided by 1.4, you will get the diameter of the objective of the lens. Is there a question? By opting higher, okay, can I take the questions at the end?
Yes, that would be good.
Yeah. So yeah. So essentially the idea is that that tells you what is the diameter of the lens. So like for instance, 135 millimeter f2 lens has a diameter of 67 millimeters. Okay. So the larger the aperture, larger the diameter. So usually so commercially people talk about this way. But when we talk about telescopes, we mention not the focal length. We don't mention 35 millimeter or 135 millimeter f2, but we would rather say 67 millimeter f2 because we care about apertures, not the focal lengths. It is a misnomer which is again created by the consumer companies, because after all we want resolution. The main thing in our astronomy is what is the resolving power of a particular objective, and resolving power depends on the diameter of the objective. So 67 millimeter will tell you how much light will this particular lens will take in. So 67 millimeter f2 will seep in much more light than 67 millimeter f4. Okay. So, but of course, the focal length would be different for these two different lenses, which you just do by multiplying 67 by 2, times 2, or 67 times 4, which would be 270. So you need lenses, generally speaking. This is what people would say. You need lenses which are which are fast lenses, f1.4 or f2. That is there. When you open it up to f1.4 or f2, the objective is really large enough. But again, take my word for it. No, it's not really necessary. Even if you have a kit lens with you, which is 1855 or something, you can use that very well. Whatever aperture, the largest aperture you have, 3.5 on it, use it. Because after all, again, this is not a normal photography. So there would be noise, and there will be noise even in f2 or fast lenses. We do not take care of these things, noise, by shelling out $4,000 from our pocket, but rather thinking it wisely by doing stacking. That is, you take large number of long exposure images and stack them to statistics, average them out, and that gives you the better signal to noise ratio. So single shots are, so even if people are starting out, single shots are no go whatsoever. Don't ever take single shots at all. They're of no use. They're not even worth hanging on a wall or something after printing. So, so a reasonable aperture is good enough. So also with fast lenses, the focal distance decrease. So like if you open it up at f1.4, you will see that it will not be able to focus objects nearby and far off simultaneously. So that also is a problem. And then people do something called compositing, which is not in one single frame anyway. So that is something. Okay, these slides are made. I thought maybe people will ask me for slides. I'll put in some information, and these are made much more as like handouts rather than for a talk. So if I go through each one of them, it'll take a long time. But to get you started, the other thing which this is something which we already know from the previous talk, that Earth is moving, so things are moving around, and one needs to track the motion of stars. And but suppose you don't really want to track, so I'll give you a ball. Suppose you're not shelling out immediately money for a tracker or something. So here's the thing: the perceived motion depends on the field of view, and so there's a rule. It's called the rule of 500. So suppose given a focal length, the exposure time for you can how long can you open up the take an exposure before you start to see stars shooting across the frame. So this is the usual formula to use. So suppose you have a 50 millimeter lens and you have a camera which is an APS-C camera. What it means is that it is there's a crop factor of 1.5 versus the full frame camera. That is like this. So the sensors have different sizes. So 36 by 24 millimeter, that is called a full frame. And then there are these APS-C sensors. So you find out which camera you have, what is the sensor. Most probably it could be APS-C sensor, which is 23.7 times 15.6. That is a crop factor of around 1.5. Okay. So you take 500 divided by 50 times crop factor of 1.5. So that gives you exposure time around 6 seconds. So you can open your lens for roughly 5 seconds before you see star trails emerging in your subexposure. So open it up for 5 seconds, and then you take large number of say 100 images for 5 seconds. But then, of course, in each image, thing would have moved around, right? So that is the reason why you need to track the objects across the sky. But if the motion is, suppose you've taken only, well, let's say you've taken 10 images. So 5-6 seconds, 10 images is like 1 minute. Things would not have moved through, I mean, would not have gone outside your frame. It would still be there. So when doing processing, when you are stacking these frames, the softwares can align your images and then add them up and take an average. So you don't have to worry about it that much. But of course, if it's a really long one, then we need to track them across the sky. So, so in any case, so this sort of tells you why you need a fast lens. If the lens is really, it's open enough, f2 or something, it will let, so 50 millimeter f2 lens will in 6 seconds get more light than 50 millimeter f3 or f4 lens, for instance, anything more. So that's why faster lenses are sort of important, but all not really necessary. Even if you take, I mean, suppose you start tracking. Once you start tracking, then you can go all night and take 1,000 images. Even if you are taking f4 at 50 millimeter f4, 1,000 images, you stack them up, you'll get an awesome signal to noise ratio. So not a thing to worry about. So also generally people will not use, so I have a lens which is f135 f2. I never use it at f2 because wide open it has these aberrations which I don't want. So I definitely will have to stop it down to f2.8 or something like that. So then the final setting. So you've chosen your lens. So your FOV is chosen. Your f number is chosen, aperture. Your timing is chosen. Then there is the question of what should be the gain. So for gain, that is the ISO, to set it up, you look at what type of image are you looking at behind in your camera when you're taking an image. It might be, so there's a histogram which sort of tells you how much photons are captured in highlights and how much are there in shadows. So essentially speaking, your image should not be overexposed. So you set up your gain accordingly, not to overexpose your image or underexpose it. You have it nicely exposed. The histogram should be a nice, smooth Gaussian. It's not really a Gaussian curve, but almost like a Gaussian curve which comes out. So then, yeah, that's of course. If it's dark, you go as high as you want. You increase the gain. People will say it again, as I mentioned, there'll be a lot of noise. Don't worry about the noise. Take many shots as you can. We'll align and stack them. So that's essentially what I already mentioned. So yeah, this is again something which I mentioned, that you will stop them down. Otherwise, there'll be aberrations. Tripod is 100% necessity. You need to buy the most stable tripod you can find, because even slight wind or vibration can ruin a lens, and a ball head which can support the weight of the camera and the lens. Again, I mentioned already about the intervalometer. That is something which you need, because you don't want to press the shutter you don't want to stand there and press the shutter all the time. So you need an intervalometer which can take images by programming. The camera apps you can use to find where you are, where the objects are. So those are necessary. And then you do something called the processing of these images. Now, I have 10 minutes. I don't want to go into too much into processing, but I'll tell you what are the, I mean, this is again, I have already told you that you do statistics, that you are aligning and stacking the subs. So I'll tell you what are the softwares which are useful for this. You can definitely look at them. So there's if you're using Windows, there's a software called Deep Sky Stacker, which works for Mac. There is Cyril, or there's also another software called ASTAP, A-S-T-A-P. And then there is also, for Windows, there's another software called Suprit, which also works. So these are the processing software or pre-processing software, basically, because these are for aligning and stacking your images. Once you've aligned and stacked your images, you'll get a pre-processed stacked TIFF file, and which you will now process according to your requirements. Because here, what we are doing is we are doing imaging. We are not doing any science. We are not doing photometry or something like that. If you want to do photometry, then there is another piece of software which can be used. In fact, Cyril has a little bit of photometry in it, and also you can process your image there. So somebody asked me a question last time. How do you know what is the right color or tint? Suppose you have taken an image of Milky Way or something. So Cyril, for instance, has a algorithm where because it knows. So there's something called it looks at the image, and there are particular stars in it. So it does what is called what's the plate solving. It does what is called plate solving. I mean, it's the name is old, because earlier astronomers had plates, which were photographic plates, and then they used to look at it and then solve them to see what are the locations of objects in there. So the same name is used. So it will do plate solving and find out what are the stars and objects in that frame or image you have taken. Okay, and it knows suppose there's a star there which is Betelgeuse. You've taken an image of Orion. It sees there's Betelgeuse in there, and it knows what type of star Betelgeuse is from the HR diagram. So there's a calibration built in. So it will set up the white balance and the colors accordingly, according to the photometry. So you'll have the actual colors rather than close to actual colors rather than anything which is haphazard. So processing softwares are also there. I mean, Cyril, as I told you, is one. Lightroom and Photoshop are used by photographers. Advanced Astro processing is done with Astro Pixel processor and PixInsight. These are the two, but these are paid softwares, both of them. I mean, not that Lightroom and Photoshop are free. Yeah. So the next thing is that you want to track the sky. I mean, in sense that now you really want long exposures. You want to track it for 4 hours, 6 hours or something, depending on how much sleep you want to lose. Or you can automate it and it will do it automatically, and you sleep over, and in the morning it will present you with the data. But then you lose out fun. So there are some trackers which are there. So there's a Skywatcher Star Adventurer, which is a star tracker. There's an Ioptron Skyguider Pro. These two are similar. Both are the same thing, almost, just different companies. And then there's a Fornax Light Track. That's a different kind of a star tracker. There's Omegon Mini Track, runs without electricity. It is mechanical. It uses spring mechanism to run. And then there is a Ioptron Smart EQ, which actually is an equatorial mount. It's a go-to mount, which means it has a computer. And you don't have to point at objects yourself. In all the above ones, you have to point at the objects or yourselves. So you need to know where an object is. This one has a computer. So it basically you tell it, hey, point me to North American Nebula, which is over here, and it will do that. Take you there. It's not very simple as it seems, but but there are ways to work through it. So okay. So then there is something called guiding. Um, it's funny how fast the time runs out. Yeah.
I think it's okay if you take a few more minutes, 10, 15, if you want.
Okay, sure. Yeah. So tracking is something where you are moving across, you're tracking these objects. But of course, when you're tracking it, it's all mechanical. I mean, they're using, it has gears and everything. So all these have their errors. So there would be backlash errors, this and that. So tracking is not always perfect. So there was something which is called guiding. Earlier, there used to be a person who was called a guider. So that person would sit at the telescope with a small finder scope, and so there would be a crosshair, and it would be kept on that object. So the moment there would be slight drift from the object, the person will actually see that there's a drift. They will do a correction on the mount. So now this is done automatically. So that's why it's called auto guiding. You have not just your own telescope, but you have another scope therein, or you can use an off-axis guider, which takes light from the same telescope and sends it to another camera, which is basically, the job is to just keep the object in the frame. And the moment it drifts here and there, it sends a signal to the mount, hey, go back to from where you have come from. So that's correction, basically, kind of thing. So that is something which we do. And then there is something called dithering, where we deliberately drift the mount by a few pixels in random directions. So that this is an interesting bit. So that essentially what it does is on every pixel, so when we drift the mount, the object will fall on different pixels now, right? Because the camera has moved slightly. Since the camera has moved, so the other pixel is now lit than the next neighbor to it. When we align and stack them, the noise, which is random noise, which can be both positive and negative, it will cancel out. So that allows removing a lot of thermal noise in the sensor that is there in the sensor itself. So then finally, since I said you are pushing your limits with a DSLR, you need to reduce your noise as close to zero as possible. There are different sources of noise. You look at each one of them. The thermal noise is controlled using cooled color cameras. So there's a cooler behind the sensor. So which you can also do for DSLR if you can make your do it yourself. I mean, make your own Peltier cooling system, which is there in the fridge and all that. So it is Peltier cooler, which you can get. It's a semiconductor device, again, which works on Peltier effect. Yeah, I like to dive into physics. Okay, so I won't dive too much here. So there's this, basically you can attach that and cool the sensor. And that takes care of the thermal noise. If you're in light polluted areas, you would use what are called filters in order to only look at sole wavelengths which you are maybe interested in. But that is for objects which are emitting those particular wavelengths. So those are narrow band targets. Then there are objects which are not really emitting, but are, as I mentioned, Pleiades last time, it's a reflection nebula. It is reflecting off light. So it's a broadband target. So it's reflecting light in all range. So you cannot use narrow band image filters there. So light pollution will definitely be there. So that can be handled in processing, or you go to a dark site. So important point, in our consumer cameras, there's a setting called high ISO noise reduction, and there is long exposure noise reduction. Find out if they have them. Most probably they do. Well, they put it there because they don't want their customers coming in and telling them, oh, there's a lot of noise here. So we don't want that automatic thing to be happening. We will turn it off, and we will do our own noise reduction, which is, as I told you, by stacking. So whenever we are taking these images, these are called lights. We call them lights because, of course, we are capturing lights. Now, there is a noise in the sensor itself. So how do you subtract it out? Well, cover the lens completely with a lens cap, and then take an exposure. Suppose you took 1 minute exposures. You take 1 minute exposures now. We'll call these images darks because there's no light in them. They're just dark images. Only fluctuations which will be there, which will be noise. So you just subtract these from the lights, light minus dark. So Deep Sky Stacker and those programs automatically do this. So you take these frames, you take light frames, you take dark frames, you supply them to the program, and it will automatically do it. But all it is doing is matrix subtraction. It's subtracting one matrix from another. Okay. So so this is essentially calibration of lights. Then there is a calibration called flats, which is that the telescopes and lenses do not illuminate the full sensor equally. There's a fall off. So you take what are called flat frames. So that's basically, it's called vignetting. Vignetting is controlled using by taking these frames, which are called flat frames. Flat frames again can be taped. You basically light up your sensor, but this time not for the exposure time, 1 minute thing, but you light up your sensor with a source of light which is equally illuminated. Okay, let's say a diffuse source of light. Blue sky is, for instance, a very diffuse source of light. Illuminate it such that your histogram is something in the middle. That is, your sensor is getting illuminated as if it is getting illuminated equally. Of course, we know it is not. So those will be your flat frames. So let's say there would be 1 second or 1/4 of a second at the same ISO and the aperture setting. So you're now changing only the shutter speed because you're now pointing at a different source, which has a lot of light. Blue sky is much brighter than dark sky. So blue sky, I mean during dawn or dusk. So it's not really heavily illuminated by sun yet. So, or you could use artificial flat panels. Use your iPad or tablet, or if you have a nice monitor which is calibrated, you open up a white presentation, bring your camera lens, just strike them close to each other, and you can take these flat frames. So these are divided in the actual subtract out the darks and you divide the flats, but the program does automatically. So these are the flat frames. Then there's also the there's some called bias frames. Bias frames are due to the sensor characteristic itself. For the new cameras, they're not really that much required. They were usually required when we use CCDs. So these are the bias frames. But then, as I said, when you're taking flats, they will also have noise. So you can also subtract dark from the flats. So those are dark flats, which are dark frames taken for the same exposure time of the flat frame. Let's say the flat frames are taken for 1 second. So you take dark frames for 1 second. Those are subtracted from the flats because you are reducing the noise. You're subtracting the noise from the flats, just like you are subtracting noise from the light frames when we subtracted light minus dark for the equal amount of exposure. Okay. So these are kind of professional setups. I mean, not really professional, amateur, but slightly more than DSLR types. So these are there. Actually, my setup is actually very similar to this. what I have. So what are typical components here? You have a telescope, also called an OTA, optical tube assembly. You use what you call a red dot finder. It allows you to look for objects, point your telescope there. I mean, because here you're not using a DSLR. Even if you're using a DSLR, it's easier to use this red dot finder. It's like that rifle scope. So Skywatcher Star Adventurer, which is a simple tracker, and an Astro Cam ASI 294 is attached over there. It's a camera which will capture light coming from the scope. There's a field flattener in between. The telescope optics are not always perfect. Field flattener is again the same thing, illuminating the frame equally. It allows that, but still one needs to take flat frames nonetheless. Then you have, as I was telling you, you have another scope, a guide scope and a guide cam, which is keeping your object in the frame and sending corrections to the mount whenever it drifts around here or there. So the mount is aligned in the equatorial direction. So where this telescope is facing at the moment, it's facing in the North Pole. So now you can move the telescope to wherever you want so I told you there are two axes, RA and dec. So polar axis is like your declination, dec, and then there's the RA. So you can move the other axis, and so the polar axis is something where around which the mount basically moves. So it tracks the objects in the sky. These are slightly more advanced stages. Just the more complex it gets. So the left-hand side is a person, I forgot the name, it's in Spain somewhere. So you have twin telescopes capturing light together, guide scope, bunch of equipment, again cameras, a computer which is controlling it, then there's a mount. On the right, you see my own setup. It's minuscule compared to that. So I have two telescopes. One is the one which was there in the previous one, and this one which is a refractor. So again, so this is here an equatorial mount. The main difference is the mount, which I told you is a go-to mount, which is computerized. You tell it where to go, it will go there. It's not so it has motors in both directions, so you don't have to manually go to a particular object. So I'll take, the field demonstration will possibly won't be possible today. But nevertheless, so if you want to delve into astronomy, what to buy and what to look for, how to see. So first thing is to know what objects are you interested in. So you can go to telescopius.com, astronomy.tools. So there are different objects. You can set up various different cameras, and it will tell you what would be the field of view you will have. Like for instance here, 350 millimeter, 36 by 24 is the sensor size camera, full frame camera. This is the Orion Nebula. This is the field of view you will get in that sensor. So that is important, because you need to know what is the field of view, because you need to know what are you interested in capturing, and accordingly what is field of view. The first thing which you so suppose you have X amount of money, the maximum amount you will have to spend is, first thing you want to allocate is to a mount, equatorial mount. This is very important. People would often buy a telescope first and then a mount. They'll buy a big telescope and they'll see that the budget they have at the moment, they cannot get a good mount, and so they'll have to compromise that. So no, first thing is an equatorial mount. Spend the maximum amount of money here, because sooner or later you'll be upgrading. Because the moment you get into this particular thing, it's addictive. I mean, and you'll get a bigger telescope or something like that, upgrade here and there. So so first thing is the mount. and you need a real good mount. There's a balance between portability and payload. I got CEM 25P. I wanted a bit of portability as well, also because I didn't buy it here in India. I bought it, so I was bringing it over anyway. So that's a different point. Anyway, the idea is to buy, um, well, not the best thing the money can buy, but the something which with a slight future in mind. So future aspects in mind. So there are good useful mounts which can take the payload capacity of around let's say 40 pounds or so, or even 60 pounds. Those are guaranteed they will last you longer. But of course, they become heavy, so they cannot be tugged around here and there easily. So if you're in a city or something, you'll have to move around. If it's an observatory, then of course buy the heaviest mount and you just set it up. So that's the option. The different options there, but this is the general advice. Yeah, I have this one. And then there are trackers, which I told you, this is just normal star trackers. So there are different ones. Astro Track, it's not available now. It's Ioptron Skyguider Pro, Star, which these other things, other three are available, and the other one which I mentioned, Omega one. I also have a tracker, which is this one, Astro Track. It's a Astro Track and Fornex Light Track are very precise star trackers. They don't even need guiding for that matter. But they have a limitation that they only run for 2 hours and you have to wind them back again to the zero position. The other ones go 24 hours. You can also make your own mount if you want. There are softwares which are used to control these mount. So there's something called EQ mod. Then there's the on-step telescope controller, and essentially they use stepper motors and can have them made. The mounts are controlled from computers, so you need certain computer to control a mount. In Linux and Mac, there's something called Indy and K-Stars Indigo, which work. And on Windows, there are drivers which are called ASCOM drivers. Now, there are different telescopes. Again, yeah, I really wish I had lots of time to discuss these things in detail.
You're welcome to come back once more.
Okay, if that's the case, then definitely I like to come back again. And
tell us when it's convenient, and we can have one more meeting.
Sure. So so today I'll just go through them rather quickly so as to have some sort of completion, and maybe next time I'll come back and mention more things here. So there are different telescopes. Each telescope has different role attached to it, and also the fact that they can do different type of stuff. I mean, you have refractors, which are like our lenses. Then you have mirror telescopes, which use mirrors, not lenses. So there's an advantage, of course. If you want, as I told you, you want you want to have high resolution telescope which look deep in the sky. So that will require large aperture. It's easy to see that large aperture, as the lenses go up bigger and bigger, they'll become very heavy. So you'll have very heavy telescopes. So mirrors are lighter. So use a mirror instead of so big mirror, 6-inch, 10-inch, 14, 20, 1 meter, and so on. And then even for us professionals, there's mirrors as a telescope which are made up of component mirrors. And there's also a recent one in Aries which is being commissioned. It's called the liquid mirror telescope, where the mirror is actually made by liquid mercury, which is on a rotating platform. So it becomes a curved surface. So that's a interesting technology. Now, so they come in different, as I said, so they come in different varieties, and each have their different uses. So, and different focal lengths. So different focal lengths are useful for different purposes. Like suppose you want to do planetary or lunar imaging. So then you need high focal length because planets are really tiny. There are nebulas which are really wide, so you can even use lenses, 85 millimeter lens, which is a wide lens. And I mean, our Orion Nebula, Orion complex, is so wide that it fits in 35 millimeter lens. So galaxies require 900 millimeter, and so there are special telescopes which are called solar scopes, which are specially made for our sun. Um, if you want to use normal telescopes, you need to use filters, white light filters in front. But these solar scopes are special in the sense that they can, suppose you want to see sun in or image or get the data of sun in H alpha. So so there are H alpha filters which we use in normal dark nighttime photography for nebulas and all that, but they are broadband. If you use them for, do not use them for sun, because sun is really bright and the whole thing will be destroyed. Here you basically single out H alpha and also, of course, other thing is that it will not give you too much resolution. So you need what are called these special solar scopes, which have etalons of cavities, which single out H alpha to angstroms, plus minus 5 or 10 angstroms. So those are the for use from there. Yes, and as I said, cameras, again, many cameras are available. So it's just uh, sort of overview of how many cameras there which can be used. So virtually any camera which you have, but again, so different cameras have different sensor characteristics. They have different sensor sizes. They have different pixel densities. Like suppose if you have a same size sensor camera, but one is 24 megapixel, the other one is 12 megapixel. So they differ in density of pixels. So they have different resolutions. So therefore you need to know something which is very important. This is even many astrophotographers, they miss out. There's something called CCD suitability. So you go to this web page again, astronomy.tools, and you can know the theory behind it as well. But this is a calculator which, if you don't know the theory, simply tells you if you have a particular telescope, you have a particular camera, whether it is really suitable combination or not. Because after all, the camera should be able to resolve it should be compatible with the resolution of the telescope, and also compatible with whatever atmospheric scene which you have. Remember, I mentioned that in my previous talk. So sort of tells you whether the camera is suitable or not. Then finally coming to the filters, as I said, you use if you want to do narrowband imaging, you use these special filters which will filter particular wavelengths, but these would be for emission nebula, which are emitting, or objects which are emitting those wavelengths, but not for diffuse objects, which are broadband objects, like even galaxies are broadband objects. As I said, these optics are not perfect, so there are these things called chroma correctors, focal reducers, which are useful. They're part of the optical train. Then we use things called dew heaters, because usually during the night, dew can settle in. So you want to control that dew. So dew heaters and controllers are used. I spoke about auto guiding. That is an extra scope there, which guides the mount. And this is about powering the setup. You basically what kind of power you need, requirements. If you want to control you need a computer also in the field or something. Now you can use a laptop or something like that. But this is a simple computer, which is a Raspberry Pi. Some of you might be familiar with it. It's a small credit card size computer, and there are softwares which you can load it up with, and it will basically run your complete system on the fly. Okay. So yeah, there are all sorts of different accessories which could be required. You want to focus your telescope, so you'll be needing some sort of a focuser. I made my own focuser. I want to save some money. Basically a motor which is attached to a telescope, which moves it back and forth. So finally, yeah, you might need also an observatory if you're doing it for a long run, because you don't want to set up the whole thing. I mean, so many things to set up. You want to don't. It takes hours to set it up before it gets dark, and then you do it. So you can also invest in an observatory. And then, as I mentioned already, these are the image processing softwares which are useful. You can plan your targets, which targets are visible when in the sky, and preferably, as I told you, which are in the at the highest in the sky, so that least amount of seeing is there, atmospheric seeing and stuff like that, and also planning their exposures when they they cross the meridian. So you need to flip your telescope, so some time will be lost in doing the meridian flip and so on. This is a setup, a starting setup which a person can get and start off doing astrophotography. Let me just grab water. Yeah. So, Madhurima, I think you asked me what would be the cost of
Yep.
setup. Yeah, so that's why I got all these things together.
Okay.
So, this sort of goes to around 300,000, 3 lakh or so.
3 lakhs. Okay.
Yes, yes. But it can be reduced if you make some things yourself.
All right.
Okay, so like for instance, these focusers and all, these power supply, these are things, I mean, I have made these things myself. So that sort of, but there's no reduction on the mount telescope than these other things. That's for sure.
Absolutely.
So, yeah. So that is where I will stop today.
Great. Suprit, seriously, this was a great talk because not everybody is willing to share these, teeny tiny details which are really important.
Yeah, yes.
I have a couple of questions. I have 3 questions, if I may ask you.
Sure.
The first one was, I know why you said it, but if you could explain the need to carry a red LED. I mean, I understand, but I think for the benefit of audience in this case.
Yeah, essentially it's for your adaptability, night adaptability of your eyes, because our pupils they dilate during the night, so any white light out, so our eyes are more sensitive to green, and red light affects our dilation of our pupil the least. So you'll still maintain your night vision while operating in the dark. You don't want someone, you don't want anything messing up with your night vision during that time. Also, of course, suddenly you look at, I mean, during the time when your pupils are dilated, if you look at a bright screen or something, it'll be a pain in the eyes.
Right, absolutely. Absolutely. The second question I had was, with regard to filters. For a person like me who does a lot of daytime photography, sometimes I find the manual filters to be both unnecessary and terrible add-on. Since there are a lot of post-processing one can do on the software.
Yeah.
Yeah. So what happens with astrophotography when it comes to filters? How crucial are they?
Yeah. So two things. In daytime photography, the filters usually what you would use are ND filters.
Yes.
And so they are useful in cases where you want to take really long exposures, like you're taking a waterfall or something like that. But I agree, these can be done also with post processing, even gradient ND filters. Now for Astro, these filters are important, not the ND filters. So these filters are narrow band filters. So suppose you are imaging from a light polluted city. But even if you're not, okay, so our camera already actually has 3 filters on top. So it has an RGB array on it. That is why we are able to make color images out of the camera.
Mm-hmm.
Now the array, so all pixels are not uniformly lit, in the sense that one pixel will have a red, and then there will be 2 green and 1 blue, and then this will repeat. So it's a bare array. Now, usually so that's why when one makes a RGB image, you need to interpolate between. So if one pixel has accepted all the red light, we need to make a full red image first. So, but the next pixel has only green. It is only after 2 or 3 pixels a green or red pixel will come. So the computer interpolates between them. So
I
you
see.
so you lose out on resolution. So that is why professionally some people actually use what are called monochrome cameras, which do not have this bare filter on top. So all therefore you are getting is luminance. You're just getting how many photons are coming on one pixel. You don't know what wavelength it is, what frequency it is of. So it is pure luminance, that is brightness. So people therefore have to use filters in front of monochrome cameras. So they would use a red filter to capture full red image, green, blue, and luminance filter where UV and IR will be cut off. So only luminance will come in. That would be black and white. So all these LRGB channels are combined. On top of it,
I know I'm repeating myself, but can't that be done post-processing? Because the luminosity conversion can be done on software, right?
oh no, you don't know how much component was in red and how much was in blue and how much was in green.
Okay. Okay.
Because light has fallen onto the pixel, we don't know the fraction, how much was in which band. So it's only when we have a filter in front, we are only getting red. So only red is passing, so it'll be so the pixel will have count of red, and then subsequently blue and green. So luminance is therefore is for what is called detail. It's not for color. So you capture a lot of luminance data, which captures all the details in the object, and then you can give it color by using the color channels and color channel. Yeah, so that um, they just color the image. That's all. But of course, when you are doing photometry, that is important. There you compute these magnitudes of various objects in different color bands, and one needs to know how many photons. You count the photons actually, and you see how many photons are there, and hence you know the brightness of the object.
No, that's really interesting because this was something that bothered me. Last question from me before we take the students' questions is, slightly more philosophical, photography philosophical, not philosophy. So conventionally speaking, in photography, you're not supposed to manipulate the image. Right. But a lot of digital photography, and I think almost all of astrophotography, depends crucially on image manipulation. That's the old adage that, don't touch a photograph, don't fiddle with it, really valid anymore? And does it hold really?
Yeah. So I can actually, let me give you an example. So let me share the screen and show you something where the manipulation. So essentially, it tells. So there are 2 kinds of manipulations. One manipulation would be that which people would do to suit their eye, that is, and so that's subjective. And even in normal photography, we know that even then, even when people used to use films, there were different processing techniques which people invented to have different effects in their photographs while processing, not just in camera, but they would be while processing. So that is true, that is there. So after all, the question is, what is the visual representation of something? Now, if someone shows me a picture of, so it's a landscape photo where there's a terrain and then there's a night sky and there's a whole lot of detailed Milky Way on top of it. Now, yeah, everyone would. Now, there would be some people who would come and crib and say, "Hey, what the heck? I mean, you don't really see these things in real life," and so it's not real visual representation. Or what do they want to convey by it? So, but that I think it's subjective in the sense. I mean, I don't know as if I see that image personally. I don't see what's the use of it. But is it conveying something to them? Maybe, maybe not. Uh, Separately, the image of Milky Way without the terrain or something might convey something, as in there's this much detail present in a galaxy, which is what is there. But yeah, so compositing, processing, they are subjective in that sense. But I can definitely, let me tell you, quantitative actual thing where processing is really important, and that too in astronomy. So the thing is called
No, because I guess one should not be deviating from what is the truth.
that's true. So yeah, so it's important when one starts to do science with it.
Right.
Okay, so like there is a fellow. Let me try to find him and a paper. So because this is important. Last time there was a question, and then I'll go to other questions. Just a sec. So
Sampurna, do you have any questions before we take the students' questions on? Oh, okay.
Okay, here is it.
Yeah.
So
I think we can't see your screen, so you need to share.
yeah.
Yeah.
So here's this guy. Is on Instagram. His name is Manuel J. Actual name is Manuel Jimenez. So he's an astrophotographer. So you ask what's the difference between a good astrophotographer and the others. So he took this image of Sombrero Galaxy,
Mm-hmm.
and he says there was a halo around it. Now, of course, the question is, so there are two questions here. One is processing, which you asked, whether it's something which is real or not, or whether it's, what was that about? Last thing which you said is, uh,
Sorry, I don't.
oh, that's fine. So the thing is, yeah, so this is, I mean, it's been processed, definitely, is whether it's truth or how far is it from the truth. So here's the thing, and this some guy comes in and says that, there was just a second. Was it in here? No, wait, I think it was here. So he put in the luminance. He's using a black and white monochrome camera. So first he put in the luminance image, and then he put in the LRGB image. So a guy here says that, hey, I don't think that is a true halo. All your stars also have these, and looks like it's a processing error combined with the refractor you're using.
Yeah.
Okay. Now, so guy doesn't know this one. So, but they are all astrophotographers, so he doesn't know what is happening here. Actually, it's a true halo. But it's brought out by processing and by actually doing science on it. So there are a whole lot of people, other people who did it using this, and they wrote a paper. So it that didn't stop exactly at just getting the image. So they did a paper, and even in the previous images of Sombrero Galaxy, this halo was visible, and they further used this guy's data, and so um, it has big images, so that's why it's taking time to load. So they used this data and found that some morphological properties of this halo.
So can I kind of understand it as the post-processing is to bring out the finer details, but not to manipulate the data to give something new that doesn't exist?
Yes. So there are two things. One is if people will use these programs like Lightroom and Photoshop, they look at what are called the higher level controls, like highlight, shadows, this and that. That can mess up with the pixels. I mean, you don't know what they're doing to the individual pixels.
Mm.
So they can mess it up wildly and take it away from the true reality. But if you want to study it scientifically, then you use pixel by pixel analysis. So this is, for instance, so this is the original discovery of photographic plate actually, and then right one is this person obtained, and so you see there is a halo. Then this halo is real, and so this was done with a 7-inch telescope, 7-inch normal refractor telescope. So, and an exposure time of 4.7 hours. And so you do something called data reduction in astronomy. So which is much more than image processing, just simple image processing as in which is we do in daylight photography, where you subtract out these things and you look at individual aperture photometry. So this is how the local background is subtracted, so I have to bring out what is the actual uh, detailed data, actual data in the hair. And so there is so they see that there is actually a stellar stream in this. Let me show you. Where was it? Yeah. So there is this circle, which is a stellar stream in this uh, galaxy's environment.
Oh, that's
Which
fascinating.
is something interesting because this galaxy does not have too much baryonic content. It is mainly illuminated by the central black hole, and there's a dust around it. So that's interesting. So besides, by the way, so
Yeah.
while I'm on it, this is my own Instagram handle where I put my own pictures.
What's your handle? Many of us are on Instagram, so we might follow you.
Okay, so it's called Astro Daily because I'm in Delhi. Astro Delights.
Astro dollars. Okay, fine. Great. So the couple of questions in the chat box, can I take them for you?
Yeah.
One of them is, Kaviraj asked, by opting for high aperture value, can we avoid using the Bahtinov mask?
No, we cannot because Bahtinov mask is still. I mean, you see that, but in order to have it focused, I mean, yes, you will when you change fiddle with your focus ring, you will see that it goes out of focus and it goes in focus. But precisely nailing the actual focus, infinity focus, Bahtinov mask is useful. I mean, here you will get the precise feel that it is at focus. Otherwise, it would be a rough one. Close to it, but rough. Then there is a question about star trails. A single long exposure or taking multiple short exposure and stacking them together. Yes, so I have taken actually star. So there are two things. One is if you are in a dark sky or something where you're taking star trails, you can take a long exposure. But of course, it is subject to there might be wind, there might be vibrations, accidental stuff which can or a plane going by or something like that which can ruin the exposure, and so your 15 minutes would be wasted. So, and also uh, in light polluted environments, there's actually a way to take star trails. So that is to take large number of short exposures and combine them together. So that is you don't set up any delay in between. As I said, set the long exposure noise reduction to 0, and then if you use Photoshop and layering, I mean this is aesthetics. Uh, Before you take a star trail, suppose there's a uh, let's say there's a bridge or something on which you're taking a star trail picture or something like that. You take one image just during the blue hour before twilight is going to set in, but blue hour is sort of at its end, not that it started. So during that time, take an image, set it as the lowest image in the layer, and then put star trails on top. Sort of, you'll get a good terrestrial as well as star trail image. my post-processed image of night sky are different in laptop monitor. Yes, that is because of calibration. Our displays are not calibrated similarly. They don't have the same sRGB color gamut. So that's why they look different in different systems. So, well, so the best thing is to have one monitor which would be best color calibrated, and then when you take it out, take the printout, it will look identical to it. Also, process the image at when you're processing in the laptop on a calibrated monitor. You process it at not at full brightness, but at slightly less brightness. So around
Does that help? Sorry?
Hmm?
How does
At
the
less
reducing the
brightness.
brightness help?
Oh, because your monitor is very bright, you will think when you're processing, you will think that the image is really bright. It actually will not be when it comes out in print.
Oh, I see. Okay.
Because we use these are mostly our LCD panels. They're not OLED. So LCD panels have a backlight on behind. So that can sort of, that's why people sometimes when they print it out, they see that the printed image is actually darker than what is there on visible on screen.
Also, I guess the shift from CMKY to RGB,
Oh.
because one of them.
Well, CMKY is how the printers print.
Yeah.
And
So
RGB is what we see. Yeah. But definitely take a look at the histogram as well when you are doing the processing. So your whites and blacks should not be flipped. So as I said, the histogram should be even. That will give you an even printout. And I usually set my brightness to around 75% or so when I am processing the image. Um, Also, so I have a calibrated monitor, but it's not really that. I mean, if you keep your eye on the histogram, it's not something which is too big of a deal. So that would do it really well. Smartphones, I can really imagine why sometimes you would see it pop out, because our usual smartphones now have what are called OLED displays, organic LEDs, which have a much more saturated content. So either you can go to your settings in your smartphone and see there are color profiles. So you can set it. Usually they set it up to pop to vivid, which pops out everything. Of course, they want everything to be sold. So you set it to slightly different value, that natural value. So you'll see it much more natural. What's the difference between CMOS and CCD sensors? Yeah, CCD sensors were originally developed. CMOS are the new ones which have come up. Scientific applications are still using CCDs. CMOS have still not been incorporated yet. They have their individual disadvantages and advantages. CMOS, as I told you, gain and ISO is something which is there in CMOS. CCDs don't have anything like gain or something. They don't suffer from it, but there are some issues in CCD sensors. There's a difference of technology. They're both charge coupled devices, actually, CMOS also, semiconductor devices. It's how they are read. I mean, as I told you, CCDs are read row by row, whereas CMOS is read pixel by pixel. And then there are some other, I mean, sort of differences between them, as in CCDs sometimes have a lot of noise, so thermal noise is there. The new CMOS sensors are less prone to noise, and uh, but CCD sensors are generally have more control than CMOS. So that's why people are in scientific applications, they're using CCD. But now CMOS are also coming in. So I hope that answers your questions.
thank you so much. Thank you, really. This was a lovely talk, and I think for many of us who like photography, this really gives us an idea of how difficult astrophotography is and what is required. Great.
No, I mean, maybe next time this would be possible if I can. I actually wanted to show you how to set this up and sort of the idea of how it happens in the field. Like,
Let's have one more session, maybe even late at night when you can really show us things.
Yeah. So basically, I do have some telescopes and cameras with me. So this is the scope which I have.
Oh, wow.
Okay, so it's one of them. That there's another, but yeah, definitely it should be for the next session.
I think we should have one more session and really take this forward. Are there any more questions or comments for today? Well, if not, is Vaishnavi, can you close the thing? So before they do it, Suprit, thank you so much.
You're welcome.
Right.
Yeah. Sorry for taking a long time.
Oh, no issues. We were enjoying it. Thank you. Vaishnavi, it's all yours.
Yes, thank you so much, Suprit sir, for this amazing two talks. And I'm sure that many who have attended both the sessions will be inspired to do sky observation and astrophotography. And special thanks to Madhurima ma'am, and thank you all for participating.
My pleasure. Thank you. And yeah, we'll be in touch and maybe one more session with you.
Sure, you're really welcome. Yeah, really appreciate it and hope you enjoyed it. You've been inspired to do it.